So let's begin with our discussion now. Today we are going to discuss about one important concept, and that is lossless joint decomposition. So before actually going to discuss or this topic of lossless joint decomposition, let us have a recap. In this unit, we are talking about normalization. Under normalization, we have covered so far few concepts, like we know now what is the meaning of functional dependency. We have seen various types of dependencies. Further, we have seen different kinds of closures, under which we have covered F plus, that is the closure of the set of functional dependencies, and also we have discussed about alpha plus, that is closure of the set of attributes. We have seen various algorithms to compute F plus and alpha plus. Further, we talked about the process of normalization. And we have gone through two normal forms. First normal form denoted as 1NF and the second normal form denoted as 2NF. If we are having a relation in UNF, that is the unnormalized form, first of all, we convert it into 1NF. Then, if the partial dependencies exist in 1NF, then we go for 2NF. But while normalizing the relations, we are following one important process, and that process is the decomposition of relations. So if my relation is in UNF, sometimes we convert the relation in UNF to 1NF by applying the process of decomposition. If we are having a relation in 1NF, and if we find the partial dependencies in 1NF relation, then we try to decompose the relation and we come up with a relation in 2NF. So the process of decomposition is simply splitting the relation in multiple relations. That is the process of decomposition. So we are having a relation and we try to split that relation into multiple relations. So this is the process called as decomposition. But whenever we are decomposing a relation, we should be very careful. And we should have a proper decomposition of the relations. So today we are going to focus upon this process of decomposition. So let us once again look at the goals of normalization and let us summarize few important concepts. So first of all, we need to decide whether a particular relation R is in good form. If it is not in good form, we need to try to minimize the redundancies so that we do not have any anomalies in our relations. In the case that a relation is not in good form, we need to decompose our relation into several relations or set of relations R1, R2 up to Rn, such that each relation is in good form or each relation is in one of the normal forms. Further, the decomposition must be lossless joint decomposition. So every relation in this set of decomposed relations, every relation should be in normalized form, and every relation, while decomposing the relation into several relations, every relation should have the property of lossless joint decomposition. And today we are going to focus upon this concept. Further, decomposition of the relation must be dependency preserving. So this is one more important concept that we are going to cover after covering the concept of lossless joint decomposition. Also, we would like to mention here that our theory is based upon two important concepts, and those are functional dependencies and multi-valued dependencies. As I stated, for the normalization other than 1NF, we are making use of a kind of functional dependency. Check whether our relation is normalized. 1NF do not require functional dependencies, but after 1NF, whichever norms, those we are going to discuss or we have discussed, those are making use of the concept of functional dependencies to check whether our relation is in normal form. And if not, once again, the notion of functional dependencies is being used to decompose the relation in one of the normal forms. So with this background, let us discuss the concept of decomposition. So let us assume now that we are having this relation schema, lending schema with 6 attributes. So this schema belongs to the banking domain. So let us assume that we are working with some banking database application. Right? We are having a schema, lending schema here with 6 attributes. What are those 6 attributes? We are having branch name, branch city, assets, customer name, loan number and amount. So let me describe all those attributes for you. So branch name is the name of the branch of the bank where the customer is having the account. Branch city represents the city where that branch is located. Assets, it is some amount, assets of that branch. Right? So whatever is the available funds with that branch, those are being stored in this attribute assets. Customer name is name of the customer who is having the account in the branch. Loan number is the number associated with the loan that is borrowed by the customer from this particular branch. And the amount is the loan amount. Right? So these are the attributes, those we are storing in this lending schema. So look at the screen. We are having one instance of this schema. So we are having branch name, we are having branch city, asset, name, loan number and amount. So if we look at one tuple of this schema or this relation, what we find is we are having a customer Jones who is having his loan with loan number L17 and loan amount 1000, and this loan is borrowed from this branch downtown located in Brooklyn City, and the assets of this branch are also given. Right? So every tuple contains this information about the branch of the bank, the customer and the loan borrowed by that customer. Right? Now, we are supposed to, this schema is not in good form. And we would like to decompose this schema. So we want to split this relation into two relations. Let us assume. Now, decompose this relation in two relations, branch customer schema and customer loan schema. So this branch customer schema is having branch name, city, assets and customer name. Whereas this another schema, customer loan schema, comprises of three attributes. And what are these three attributes? Customer name, loan number and amount. So this original schema, that is lending schema with 6 attributes, is now being decomposed into two relations, branch customer and customer loan, and the respective attributes are being shown in these relations. So branch customer is having these 4 attributes, whereas customer loan relation is having 3 attributes. So this is the way how we have decomposed our relations. Now, whether we would like to find out whether this decomposition is good decomposition. Right? So, what we are going to do next is, see here, we are having this original instance of lending schema with 6 attributes, right? And we are having this decomposition, wherein we are having two relations. Those are decomposed. So original relation is being decomposed into two relations, right? And now we are having these two respective relations, branch customer and customer loan. Now, whenever we perform some operations, whenever we need to extract the data from the relations, the most popular operation that we need to perform is the join operation on the relations. So we have seen this operation earlier whenever we discussed SQL, right? So many times we need to perform the join operation on relations so that we can collect the information from various relations and come up with the required data. Right? Now, if we have decomposed this relation into two relations, right? And if now we would like to perform the natural join of these two relations, branch customer and customer loan. So in our relational schema, we are having these two relations now, branch customer and customer loan. And we want to perform now natural join of these two relations. So let us try to perform the natural join of branch customer and customer loan relations. So we have seen the definition of natural join. So what we do in natural join? Natural join actually joins two relations such that whichever is the common attribute in these two relations, this common attribute matches, or the value of that common attribute is same. So whichever are the tuples from these two relations for which the common attribute matches with the values, then such data is being extracted in our natural join. Right? So, if we would like to perform the natural join of these two relations, obviously what will happen? the system will check which is the common attribute in both the relations. So which is the common attribute in these two relations? Yes. Which is the common attribute? Customer name. Yes. So we are having this customer name which is common in both of these relations. So what will happen? The first tuple from branch customer is picked up, right? So customer name is Jones. So what will happen in natural join? The other relation is checked, and whichever tuples, those are having the same customer name, those will be matched. So here the customer name is Jones. So we are having in customer loan relation two tuples with the same name Jones. So this tuple is concatenated with this tuple because customer name is same. Also this tuple is combined or concatenated with this another tuple as well because the customer name is same. Right? Similarly, for every tuple, the same criteria is being applied. So if the second tuple is considered, the customer name is Smith. So all the tuples in the other relation with customer number Smith are being matched. So here we are having only one such tuple. So this tuple gets matched. Right? Now, let us see one more tuple. So this is the third tuple from branch customer and the customer name is Hayes. So in customer loan relation, we are having two tuples with the same name, Hayes. So these tuples are being matched. Right? So likewise, we are computing the result of our natural join. So after following such kind of a process, our system will provide us the output of natural join like this. So see here, the first tuple from branch customer having the attribute values downtown Brooklyn, this asset value which is 90 lakhs and Jones. So downtown Brooklyn 19 lakhs and Jones. So this first tuple from branch customer relation, right? Now this tuple is matched with the tuples from customer loan, and as we have seen, we are having two tuples in customer loan with same name. Right? So both of these tuples will be matched. So we are having here the combination. So customer name will appear only once because it is the same name. Then this loan number L17 and this amount that is 1000. Right? So we are having other tuple also. So these values will remain same. And the tuple with loan number L93 and the amount 500 is being matched, right? So we'll be having now these two tuples, matching tuples for this first tuple in branch customer. So we are having now this data. That is the output of our natural join. Now, this is our original data and this is the outcome of the natural join of these two decomposed relations. Now, let us try to check whether we are having any spurious tuples in this natural join of these two relations. What I mean by spurious tuples? The spurious tuples are the unwanted tuples or the invalid data that we may have. that is not there actually in our original relation. But in my join, having such a data that is not at all existent. The data that do not exist in our original relation. So if I compare this original data with the output of this natural join, then what I find is, I find that few of the tuples are not actually valid tuples. So the customer Jones is having the loan in downtown branch with loan number L17, and other customer Jones is having the loan with loan number L93 in the branch Miamis. But as there are two tuples having the same name, right, and our common attribute is customer name, these two relations are being matched with the attribute customer name, and this is the reason why we are having this tuple, which is actually invalid. So customer Jones is not having, so customer Jones with loan number L93 is not having the loan in downtown, but Jones with loan number L93 is having the loan with the branch Miamis and not with branch downtown. So this particular tuple is invalid. This tuple does not exist actually in my original data, right? So this is the spurious tuple. Similarly, I can find out few more tuples which are actually invalid. So that data is not valid, right? So in this branch customer natural join customer loan, we are having some data which is invalid. We are having some spurious tuples, and that is why we say that this decomposition, branch customer and customer loan, is lossy join decomposition. So we are saying that some information is being lost, or some information in this join is invalid, and that is why we say that this decomposition is lossy join decomposition, and we do not want such kind of decomposition. So whenever we try to decompose the relation, we should come up with a decomposition which is having exactly the same data that was present earlier. We do not want any invalid data in the natural join of the decomposed relations. And that is the reason why such kind of a decomposition is not correct. Right? Are you getting me?
Yes, ma'am.
So, to further illustrate this concept, I'm just summarizing the things. We had this original schema, lending schema. We decomposed this schema into branch customer schema and customer loan schema. We have now a conclusion that this decomposition is lossy decomposition or lossy join decomposition, because the original data is not being preserved as it is, right? So the instances, we should be very careful while decomposing our relation. So careless decomposition of a relation may lead to another form of bad design, and we need to avoid such kind of bad design. So, please remember, while decomposing a relation, we should be very careful. So, careless decomposition of relation may lead us to another form of bad design, and this should not happen. So, what to do? So, here is the concept of lossless join decomposition. So, now let us see another way of decomposing the same relation lending schema. So, now this lending schema is being decomposed into two relations once again. And in these two relations, we are having branch schema with three attributes: branch name, branch city, and assets. And we are having another schema, loan info schema, which is having four attributes: customer name, loan number, branch name, and amount. So, the same lending schema now is being decomposed in some other way, right? Branch schema and loan info schema. So, obviously, we are having some common attribute in these two relations. So, what is the common attribute in these two relations? Yes? Which is the common attribute in branch schema and
branch name. Branch name.
Branch name. Yes. So, branch name is the common attribute now in these two schema. And this is the way how we have decomposed our original schema. Right? Now, one important point to be noted here. Whenever we try to decompose any relation schema R into, say, relations R1 and R2, then all the attributes of original schema R must appear in the decomposition R1 and R2. Meaning, our original schema R is union of R1 and R2. What is R1? This schema. Right? So, set of attributes. What is R2? This schema. So, once again, set of attributes. Schema is nothing but set of attributes. And this lending schema is my R here. So, this is my R, this is my R1, and this is my R2. Right? So, while decomposing any relation into two relations, say R1 and R2, we need to make sure that all the attributes of original schema are there either in R1 or R2. So, we always need to check this condition where R1 union R2 is giving me original schema R. Right? So, that is the first condition that we need to check while decomposing the relation. What next? We need to check whether our decomposition is lossless joint decomposition, because we have seen the disadvantage of lossy decomposition, and we do not want that lossy decomposition, right? Because we cannot preserve the original data in our lossy decomposition. So ideally, we should come up with lossless joint decomposition. So, what do we mean by lossless joint decomposition? See here, for all possible relations small r on schema capital R. This expression must be followed. This expression must be satisfied. So what this relation says? See here, R is being decomposed into R1 and R2. So R1 is having some attributes and R2 is having some attributes. Okay, now what we are saying is we are having now the relations on these schemas. So relation on this capital R is say small r. The relation in this schema R1 is say small r1. And the relation on this schema R2 is say small r2. While decomposing the relations, right, the first condition that we need to follow is R, capital R, that is the original schema, should be union of R1 and R2. R1 is the schema for decomposed relation. R2 is also the schema for another decomposed relation. So always R1 union R2 should provide us the original schema R. And the second condition that we need to follow for having lossless joint decomposition is R must be equal to projection of R with respect to attributes R1 and projection of R with respect to attributes R2. If we consider this projection, this will provide me one relation. If consider this projection, this will provide me another relation. Right? So let us assume that these two relations are R1 and R2. So R1 is the relation like we are projecting our R with respect to the attributes in schema R1. The relation R2 is like we are projecting our original relation R with respect to the attributes of schema R2. So if we are having these two relations and if I try to find the natural join of these two relations, this should provide me the original relation R. So this is the condition that we need to satisfy for lossless joint decomposition. So splitting of relation R, decomposing of relation R into two relations R1 and R2, and then having the natural join of these two relations will provide me exactly the same relation that I had earlier. And if this is the case, then we say that this is a lossless joint decomposition. Right? Now, let us see how we are going to test it in practice. So, a decomposition of into R1 and R2 is lossless join if and only if at least one of the following dependencies exist in my closure F plus. So what is the dependency? R1 intersection R2 should determine R1 or R1 intersection R2 should determine R2. What does this mean? What is R2? R1 intersection R2 is actually providing me the common attributes in R1 and R2. Do you agree with me? What is R1 intersection R2? Yes? What is R1 intersection R2? R1 intersection R2 should provide me the common attributes in these relations R1 and R2. Right? So if I am having this relation schema R1 and this relation schema R2, what I'll get in R1 intersection R2? What I'll be having? For this example? Yes?
Branch name.
Branch name? Yes, correct. So branch name is common in R1 and R2. So R1 intersection R2, in this example, we will get branch name. Right? So we are right now talking about a condition or how practically we can find out whether our decomposition is lossless joint decomposition or not. A decomposition of R into R1 and R2 is lossless joint decomposition if and only if at least one of these dependencies are present in our F plus. F plus is our closure of set of functional dependencies. So what we are saying is either R1 intersection R2 determines R1 or R1 intersection R2 determines R2. What does this mean? R1 intersection R2 is actually giving us the common attribute. In our example, it is branch name. Right? So whichever are the common attributes in the decomposed relation, these common attributes should either be the super key of R1 or it should be the super key of R2. See here, we have seen the functional dependency of the form K determines R. R is my relation schema. So if some set of attributes is determining all the attributes in the relation, then we say that this is my super key. We have seen this earlier. Right? So similarly, we are saying here, whatever is the intersection of R1 and R2, meaning whatever is the set of attributes, those are common in both R1 and R2. That must be either the super key of the decomposed relation R1 or the super key of the decomposed relation R2. So in other words, we may say that if R1 intersection R2 forms a super key of either R1 or R2, the decomposition R is a lossless joint decomposition. I'll repeat. If R1 intersection R2 forms a super key of either R1 or R2, the decomposition of R is a lossless joint decomposition. So please note down this important concept. When we are going to say that our decomposition is lossless joint decomposition, we need to find out R1 intersection R2 and whatever is there in this set R1 intersection R2. If this is either the primary or either the super key of this R1 or super key of this R2, then we say that this is a lossless joint decomposition. So with the same example, I'm going to illustrate this concept. We have this lending schema and we have decomposed our lending schema into branch schema and loan info schema. So we are having now the functional dependencies like branch name determining branch city and asset. So if we know branch name, it is possible for us to determine where that branch exists or what is the location, what is the city where that branch is located. So branch name can determine branch city. Also, branch name can determine the assets with that branch. Right? So branch name determines branch city assets, and if we augment branch name to both the sides, we may say that branch name determines branch name, branch city and assets. So branch name is determining all the attributes of this relation branch schema. Right? So for this schema, branch name is my primary key or branch name is my super key, because this attribute is determining all other attributes. Okay, now condition, we need to find out the intersection of these two schemas, branch schema and loan info schema. And as we have seen, the intersection of these two sets of attributes is branch name. Okay, and right now we have seen that this branch name is the super key for this relation schema, branch schema. Right? So the condition that we have stated is either R1 intersection R2 should determine R1, or my R1 intersection R2 should determine R2. Here, if this schema is my R1 and if this schema is R2, what is R1 intersection R2? R1 intersection R2 is giving me this branch name. And what we find is this branch name is determining R1. Branch name is determining my branch schema. Branch name is determining R1. So in this example, my R1 intersection R2 is determining this R1. So this condition is satisfied. Right? And that is why we are saying that this decomposition is lossless joint decomposition. Right? So we have seen earlier that lending schema was decomposed carelessly and we came across the lossy decomposition. But now whenever the lending schema is decomposed into these two relations, branch schema and loan schema, we find that this decomposition is lossless joint decomposition. So if we are having the natural join of these two relations, we will be getting the original relation, that is the lending schema. Okay? So I hope you must have understood the concept. If I am having original relation schema capital R and the relation small r, if this relation gets decomposed in R1 and R2, and if I am having say relation instance R1 with respect to this schema capital R1 and the relation instance R2 with respect to this schema R2, and if I try to find out the natural join of R1 and R2, I should get the original relation R without loss. And if this is the case, then we say that our decomposition is lossless joint decomposition. And to test it practically, we are having here one simple test. What we are going to do is, we are going to find out the common attribute or common attributes from the set of relations. So whatever is the common attribute, if that common attribute forms the super key for either relation 1 or relation 2, then we say that it is lossless joint decomposition. So this is very important condition to check whether our relation is lossy or lossless. Okay, now further, this relation loan info schema can be decomposed in two relations, loan schema and borrower schema. And once again, you may find that this decomposition is also lossless joint decomposition. So, lending schema is decomposed as branch schema, loan info schema, and further this loan info schema can be decomposed as loan schema and borrower schema. Right? So, ultimately in our design we will be having this branch schema, this loan schema and this borrower schema. And we find that we have seen that this decomposition is lossless joint decomposition. Similarly, if we try to find out the decomposition for this schema, we come up with loan schema and borrower schema. And if we try to find out whether this decomposition is lossless joint decomposition, we can prove that, right, by using the same condition, R1 intersection R2 either determines R1, R1 intersection R2 determines R2. So what is the common attribute in these two relations? In these two relations, the common attribute is, what is the common attribute? Yes?
Loan number.
Loan number. So you need to prove now that loan number is the super key for loan schema, or loan number is the super key for borrower schema. So either this loan number should be the super key of loan schema, or this should be the super key of borrower schema. And if this is the case, then we may say that this decomposition is lossless joint decomposition. And what we find here is loan number is actually determining branch name and loan number is determining amount. So loan number is super key for this schema, loan schema. And that is why we may prove that this decomposition is also lossless joint decomposition. Right? So this is really very important concept, and we are going to use this concept while decomposing the relations in our higher normal forms. Right? So you should understand what this concept is, lossless joint decomposition. So I think we have enough discussion regarding this concept. So I would appeal you to once again go through these contents, right? So that it would be easier for you to understand the concepts in the next class. Right? So in the next class, we are going to discuss one more important concept, and that is dependency preservation. Right? And further, we are going to make use of these concepts, lossless joint decomposition and dependency preservation, while discussing the higher normal forms. So let's conclude the session today. Thank you.